Well, for the exercise today, I want to take a look at a pretty cool place that's fairly well known and fairly mysterious. This is Stonehenge, and it's a collection of rocks that are arranged in circles, and actually there are several circles that are set up here. This is the outermost one, but there's some inner ones, and there are a variety of others that you can't see in this photograph that have been partially destroyed. And so this is a mysterious thing about how this structure got here. It was built back 2600 BC or thereabouts. These stones here are called sarsens. They're made out of actually these guys here are sarsens, and they're sandstones that come from several kilometers away. And there are also structures here that are made out of dolerite, a mafic igneous rock that comes from much further away. They're smaller than these guys, but they're still quite large. And so one of the mysteries is, how do they get these large stones here and then build this structure? You can see this picture from you can see the scale. These are people standing around. It looks like maybe, I don't know if that's a, well, yeah, it's probably not a. I thought at first maybe that was a woman getting married, but looks like she's got a backpack on, so she's probably not getting married. But anyway, for scale, maybe a couple of meters, so it's maybe like 5 meters tall, and that's about 5 meters across, and looks like spacing about a meter or two. Here, this gap between them, and so um, so there are the structures, these posts, these columns, and then these beams or a plate that is sitting on top. The beams are about 3 meters long, and about a half a meter thick, and about 1.5 meter spacing. Although you can see that they are somewhat different. There, that one looks like it's a bit of a bigger size than these guys. So there's some variability. So there are a lot of mysteries about Stonehenge, how it was built, what it does, what its purpose was. You've probably seen pictures of the solstice sun rising coming through one of these things, and so maybe it's a calendar. Um, Not really quite clear. The question that I want to pose, though, is a little bit simpler. We have these beams here, and you can see there are quite a few of them that are still standing. And so, how do you design a beam so it lasts for such a long time? This thing is under stress from the gravity, from the body force, from its weight. And so, how do you design that thing so that it will last such a long time? And so, the way to do that, I think, is to set up an analysis of this thing as a beam. And so we'll take this picture. Actually, there you can see a nice picture of at least the full moon is lining up with something. So I'm not sure what significance that has, but we'll use this to form our conceptual model. And so what I did is said, that's the beam that I'm interested in. That's the dimensions, and it seems to be just resting on these columns here. And so there's some friction there, but I'm going to assume that it's a roller type bearing, so it can move from side to side. Um, and then we'll load it with a body force. So here's the size of the beam that we'll assume. In order to get this analysis to solve, we have to prevent it from moving this way. Actually, prevent it from moving this way. The rollers will prevent it from moving this way, but not this way. So I'll fix it at a single point right here, and I'll show you that in a second. Um, so there's the dimensions, and then we need some properties. So I went and looked up the properties of sandstone, And as you might imagine, there's some variability. It depends on the degree of cementation and what the cement is made of, and so forth. But the range for the modulus is the Young's modulus is between 1 and 20 gigapascals. So I'm just going to use the middle of the road value here. And the density is this number here, 2,000 kilograms per cubic meter, so twice that of water. Poisson's ratio is covers this range, and we'll use that value. And the tensile strength of sandstone is between 10 and 30 megapascals. So dolerite, this is an igneous rock, a mafic igneous rock, and so the porosity is much lower. The elastic modulus is higher. This is the range, and so the middle of that range is 40 compared to 10. And the density is also greater. It's 3,000 kilograms per meter cubed. Poisson's ratio is a bit lower range, although these ranges certainly overlap, but the range is lower, and so the median value here is we'll take as just 0.2. Interesting though, the tensile strength is about the same. Now, what we'll do then is to take a look at, well, we'll use these properties, we'll set up an analysis, and we'll take a look at the distribution of stresses. So let's switch over to the analysis. I just have one parameter, the thickness, and three variables, these different material properties. That's the Young's modulus, the density, and the Poisson's ratio. And point probe is going to be right here, right in the middle on the bottom. And I'll show you why that is in just a second. So the geometry is just this rectangle, and I'm going to put 3 points here, and I'll use that to set up the boundary conditions. So we said that there's a 1.5, well, the whole thing is 3 meters. That's going to be 3/4 of a meter and 3/4 of a meter in a 1.5 meter span. And there's the points. And so it's a linear elastic material, and I use the properties that I just showed you. And the boundary conditions are rollers here, and I put those points in so that I can specify the boundaries over this interval. The point really is the end of that boundary condition. And then I have a fixed constraint right here, so that point does not move, although the rollers can slide. And then the body force here over the whole beam, and it's just rho times g, and g underscore const is the built-in gravitational constant. So the mesh, it's fine, or I guess extra fine. The default is really quite coarse. And we go ahead and run it. And here is the this is a plot of the first principle stress, and you can see it's a deformed plot. It shows this beam sagging. The roller boundaries you can see here prevent there from being any deflection. Probably what would happen is this would sag down and this end would lift up a little bit, but this is showing that it's in contact the whole way, and that may well be how it works. What we see is that the maximum principal stress has this kind of W-shaped pattern. Well, maybe upside down W. Maybe it's an M. It's an M. Yeah. So maybe yeah. And so there's the maximum right there, and there's also some high stresses right here. And now remember, when it's positive, it's tensile. So what's happening is this beam is bending like that on the outside of this kind of concave bend, we have maximum tension right here. And then this also is a bend. We have a negative curvature here, and on the outside of that, uh, right there is the maximum tensile stress along the top of this beam here. Okay, well, the significance of this is that the strength of most materials is less in tension than in compression. This is certainly true for rock. So we're interested in this stress, this tensile stress, because the place where we're vulnerable is, I think, the way that this is most likely to fail. If the whole thing just doesn't topple over, the way this beam is most likely to fail is to break and crack right down the middle. And the way that would happen is if the stresses exceeded the tensile strength right here at this particular point. Okay, so what that means is we can use the stresses at this point as really a monitor for the condition of this whole beam. All right, so that's why I put in this domain point right here, so I can keep track of the stresses at that point of vulnerability. Okay, so what I want to do, the question I want to pose is how thick should we make the beam? The default here was 1/2 meter, but what would be the optimal thickness? And so what I did was to try different values, and let's see if we so I can evaluate this point probe, and I can do this. Let's do the first principle stress. So there's the first principle stress. So 40,000 pascals. And let's go ahead and change then the thickness. So here the thickness was 0.5, and let's make it 0.7. And let's go ahead and rerun that. If I change the parameter, the way I had this set up, the 0.7 was in the geometry right there. So I change it, changes the geometry, gives me the new result. There it is. And the last one was 40,000, and you can see this is going to be a bit less. The maximum there is, it's 36,000. So we made it thicker, and we reduced the stresses here at the tip, or right here at the center. So that's encouraging. And so let's try this again, and let's make it a good bit thicker. So make it 1.5 meters thick, and we'll try that. Okay, so it's much thicker now. And what we get here is now the stresses have increased. The previous one was 36, but now you can see we're up at 63 times 10 to the fourth, or 6.3 times 10 to the fourth. So we're getting bigger stresses. And so I think what's happening here is if we make let's go and do an extreme case. So if we make it quite thin, then we get high stresses here and high stresses here. And what's happening is when it's quite thin, it's curving a lot, and when it curves, the curvature causes fiber stress, and that curvature cause there to be stress on the outside of this curve. So the as it gets thinner, it bends more. That creates stresses. As it gets thicker, though, it gets heavier, and just the sheer size of the load increases the stress. And so there's a happy medium where it's not too thin, not too thick. And so what we want to do is to try to find that happy medium, and that would be the optimal thickness to make this beam. So what I did was to set this up as an optimization problem. And I made a study where I did this, and I just right clicked and used this optimization capability, and I set it up so that this parameter is what I'm going to optimize, the thickness, and I bound it here with lower and upper bounds. So I did just some experimenting, and I found that it it was this was pretty high and this was pretty high, and values between these numbers were lower. So I figured it's got to be in there someplace, and I give it an initial guess. So probably best to guess someplace in between the bounds. And then I need up here to enter the objective expression. And what's going to happen is that it will take this expression, and if I set it here on minimize, it will try to make this as small as possible. Well, this term here is my domain point probe, and I have it set up to give the first principle stress. And so when this is large, I have tension, and so I set this up so that by making that as small as possible, I'm making the tension at the bottom of the center of this device or this beam as small as possible. Okay, so that's really all there was to setting this up. I needed to do some initial experiments to bound it, but then I could go ahead and give an initial guess between the bounds, do this objective function, and I'm ready to go. So we can go ahead and run this, and it'll print out the point probes as it goes. Actually, this is kind of cool. So what it's doing, you can see it. Well, I don't know if you can see it here, but let's go and try that again. I'm going to run that again. It runs pretty quick, but we can see, I think, a nice feature of this. So we'll turn on the point probe. So this is the stress here, and we're trying to minimize it. This is the thickness. Tried this guess, then this guess, and it's going back and forth trying these different guesses. And it connects this graph with a line. But what you end up with then, if you ignore the lines that are connecting these points, you end up with a curve that's like this. So this is the objective function, which is the principal stress, and we can see when it's small, the thickness is small, it's bending too much, we get high stresses. When it's thick, the load is too great. But right here is the optimal point, 0.7 something. We can go and print it out here. So we can just use a point evaluation, give it a thickness, and it's 0.734 is the optimal thickness to make your beam if you want to keep the stresses as small as possible. So we have the optimal beam thickness for a sandstone. Evidently, those beams were all made out of sandstone, and that 0.7 meters, it's kind of hard to measure accurately from the photographs, and I couldn't find any accurate measurements in the material that I could locate on Stonehenge, although I'm sure that they have all of those stones measured quite accurately. But it seems like a reasonable thickness. So it seems like those druids or whoever it was that built the Stonehenge blocks knew what they were doing. They're making blocks that are about the optimal thickness. So one thing that was curious was that the sandstone was used in the big blocks, the big spans. Dolerite was used for smaller structures. It was not used for the big ones. And the properties of dolerite are a bit different. And so I wondered why this might be. And so what I would suggest that you do is see if you can figure out why that could be. And I mean, there are a variety of explanations. Perhaps they were just built at different ages or had some different significance. The rocks had some different significance. I don't know. I don't know those aspects. But just strictly from a mechanical point of view, why would sandstone be preferred for large structures, whereas over dolerite, basically?